Welcome to this coding walkthrough. Today, we'll dive into an interesting problem titled Check Array Formation through Concatenation. We'll explore the problem statement, discuss potential approaches, and analyze the efficiency of our solution. Let's get started. In this problem, you are given an array of distinct integers called ARR, as well as a 2D array called pieces, where each element in pieces is itself a subarray of distinct integers. Your task is to determine if it is possible to form the array ARR by concatenating these subarrays in any order. However, there is one important restriction: you cannot reorder the integers within any subarray in pieces. Essentially, the order of elements within each subarray must remain the same. The function should return true if the array ARR can be formed under these conditions, and false otherwise. The input includes an array ARR with a length of at least 1 and at most 100. And a 2D array pieces with up to 100 subarrays. The output is a Boolean value that indicates whether the array can be formed as described. Let's look at some examples to clarify. In the first example, the input is ARR equals 85 and pieces equals 85. Here, the array ARR contains only one element, which matches exactly with the single subarray in pieces. Since no reordering is needed and the subarray matches perfectly, the output is true. In the second example, the input is ARR equals 15, 88, and pieces equals 88, 15. Although the subarrays in pieces are provided in a different order, we can concatenate them as 15 plus 88 to form the array ARR. Since it is possible to form ARR by following the problem's rules, the output is also true. Now, consider the third example where ARR equals 49, 18, 16, and pieces equals 16, 18, 49. In this case, the only subarray in pieces is 16, 18, 49, but its order does not match the order of elements in ARR. Since we are not allowed to rearrange the order of elements within any subarray, it is impossible to form ARR using this pieces array. Therefore, the output is false. This highlights the importance of matching both the order of elements within each subarray and the overall sequence of ARR. In the fourth example, we have RR equals 91, 4, 64, 78, and pieces equals 78, 4, 64, 91. Here, we can concatenate the subarrays 91, 4, 64, and 78 in the order 91 plus 4, 64 plus 78 to form the array ARR. Since this is a valid way to construct ARR while respecting the order of elements within each subarray, the output is true. This example shows that while the subarrays in pieces can appear in any order relative to one another, their internal order must remain intact. Finally, let's review some important constraints and edge cases. The elements in ARR are always distinct, and the elements within each subarray in pieces are also distinct. If ARR contains only one element, it must exactly match one subarray in pieces. If the total number of elements across all subarrays in pieces does not match the length of ARR, the output must be false. Additionally, any subarrays in pieces that contain elements not present in ARR will lead to a result of false. These details ensure that the problem's requirements are met and help clarify how to handle edge cases effectively. To begin, let's consider the brute force approach as a starting point. The main idea here is to directly iterate through the ARR and check if each subarray in pieces matches a subarray of ARR. For each subarray in pieces, we manually look for its placement within ARR by iterating through the elements of ARR. If we find a match, we move on to the next subarray in pieces. However, if we fail to locate a match at any point, we immediately return false. The complexity of this approach is determined by the number of subarrays in pieces and the average length of each subarray, which results in a time complexity of O(k*m). While this approach is conceptually simple, it can be computationally expensive for larger inputs due to repeated scans of ARR for each subarray. Now, let's move to the optimized solution using a hash map. The hash map approach is built on a few key observations. First, every integer in ARR is distinct and belongs to at most one subarray in pieces. Second, the order of integers in ARR must align with the order of subarrays from pieces. Using these properties, we can efficiently determine where each subarray in pieces should appear within ARR by leveraging a dictionary for quick lookups. The strategy is to create a hash map, pieces_map, where the key is the first element of each subarray in pieces and the value is the subarray itself. This allows us to quickly access any subarray in pieces by its starting integer. As we iterate through ARR, we use the hash map to check if the current element in ARR corresponds to the beginning of a subarray in pieces. If a match is found, we verify the subarray matches ARR at the current position. If there's any mismatch, the process halts, and we return false. Otherwise, we continue until all elements in ARR are processed. This approach improves efficiency significantly, reducing the time complexity to O, n plus k, where n is the length of RR and k is the total number of elements in pieces. The space complexity is also manageable at O, k, thanks to the hash map. Finally, let's briefly touch on alternative approaches and why the hash map strategy is preferred. One possible alternative is the two-pointer technique, which involves simultaneously iterating through ARR in pieces. However, this method requires additional logic to align the subarray order, resulting in complexity and inefficiency due to frequent pointer resets. Another alternative is sorting both ARR and pieces to check for matching subarrays, but this breaks the strict order requirements of ARR, making it infeasible. Ultimately, the hash map approach stands out as the best choice. It is efficient, avoiding redundant checks and enabling constant time lookups for subarray matching. It is also straightforward to implement, sidestepping the need for complex pointer manipulations, and it guarantees correctness by directly comparing subarrays to ensure both order and content constraints are satisfied. While the brute force approach is simpler conceptually, it's computationally expensive, and though the two-pointer technique is memory efficient, it's less intuitive and more error-prone. The hash map approach provides the optimal balance of clarity, efficiency, and correctness, making it the ideal solution for this problem. To understand the problem, consider that we are given an array ARR and a list of arrays called pieces. Our task is to determine whether we can reconstruct ARR by concatenating all the arrays in pieces in any order. The important constraint here is that the elements within each subarray in pieces must remain in their original order. The brute force approach to solving this involves checking whether each subarray from pieces matches a contiguous segment in ARR. The process starts by initializing a pointer I to traverse ARR. For each subarray in pieces, we compare it with a segment of ARR starting from the current pointer. If all subarrays match perfectly with non-overlapping segments of ARR, we return true. Otherwise, we return false if any mismatch occurs. If a subarray from pieces matches the corresponding segment of ARR, we increment the pointer by the length of the matched subarray and proceed to the next subarray. However, if it does not match, we shift the pointer in ARR by one position and attempt to find the match again. This process continues until either the subarray is matched or the end of ARR is reached. Finally, once all subarrays have been checked, we verify whether the entire pieces list was successfully matched to non-overlapping segments of ARR. If so, we return true. Otherwise, if any subarray cannot be matched or overlaps occur, we return false. For example, if ARR is 85, 1, 2, 3, and pieces is 85, 1, 2, 3, we start with the first subarray, 85, and check if it matches ARR, 0:1. Since it does, we move the pointer to the next position. Next, we take the subarray, 1, 2, from pieces and check if it matches the segment ARR, 1:3. It matches successfully, so we advance the pointer again. Finally, for the subarray, 3, we check if it matches ARR, 3:4. This is a match as well, meaning ARR can be fully reconstructed by concatenating the subarrays in pieces. Therefore, we return true. Some key insights to note here include the importance of preserving the order within each subarray, which simplifies the problem by ensuring that we don't need to consider permutations of elements. Additionally, ensuring that the segments in ARR are non-overlapping makes the matching process deterministic. Lastly, we can terminate early if any subarray fails to match a segment in ARR, saving unnecessary computations. To handle edge cases, we must consider several scenarios. If pieces contains a subarray that does not exist in ARR, we immediately return false. Similarly, if ARR contains elements that are not covered by any subarray in pieces, it is impossible to reconstruct ARR, so we return false. On the other hand, if pieces is empty, it is trivially valid since there are no subarrays to match, and we return true. The data structures we use can play a significant role in optimizing our approach. Using pointers or indices to traverse ARR allows us to efficiently check for matches without creating unnecessary copies of subarrays. Additionally, a hash map can be used to store the starting value of each subarray in pieces, enabling faster lookups when traversing ARR. Analyzing the complexity of the brute force approach, the time complexity is n*(m), where n is the length of ARR and m is the total length of all subarrays in pieces. This is because, in the worst case, we may need to compare each subarray from pieces with multiple portions of ARR. The space complexity is 1, since no additional data structures are required beyond the pointers. To optimize this, we can use a hash map to pre-compute a mapping from the starting value of each subarray in pieces to the subarray itself. This avoids repetitive comparisons and reduces redundancy. Furthermore, we can implement an early exit strategy to terminate the process as soon as a subarray fails to match, saving unnecessary computations. With the hash map approach, we can optimize the algorithm significantly. In this method, we first create a hash map where each key is the starting value of a subarray in pieces, and the corresponding value is the subarray itself. Then, as we traverse ARR, we check whether the current value in ARR exists in the hash map. If it does, we retrieve the corresponding subarray and verify whether the segment of ARR starting at the current index matches the subarray. If it does not, we return false. Otherwise, we skip over the matched segment in ARR by adjusting the pointer. Once we finish traversing ARR, if all subarrays are successfully matched, we return true. This approach minimizes redundant comparisons and ensures that the solution is both efficient and easy to implement. This Python solution solves LeetCode problem number 1640, check array formation through concatenation. The goal is to determine if the array ARR can be formed by concatenating subarrays from the pieces list in any order, while preserving the order within each subarray. The function canFormArray starts by creating a dictionary, piece_map, that maps the first element of each subarray in pieces to the subarray itself. This allows for quick lookups based on the first element of any piece. Next, the function initializes an index I to traverse the array ARR. It iterates through ARR while checking if the current element matches the first element of any piece in pieces. If no matching piece is found, the function immediately returns false. When a match is found, the corresponding piece is retrieved from the dictionary, and the function checks if the segment of ARR starting at I matches this piece. If the segment does not match, the function returns false. If the segment matches, the index I is advanced by the length of the piece, and the process continues until the end of ARR. If all segments match their corresponding pieces, the function returns true. This approach ensures that the solution is efficient, as the dictionary lookup and slicing operations enable quick validation of matches. The algorithm handles edge cases, such as mismatched elements or extra elements in ARR, by returning false immediately when an inconsistency is detected. Here, we start by importing the necessary packages and defining our solution class with a method named canFormArray. The goal of this method is to determine if the array ARR can be formed by concatenating subarrays from the pieces array exactly as they are. The first step is to create a map that associates the first element of each piece with the piece itself. This allows us to quickly look up which piece corresponds to any given starting value in ARR. Next, we traverse the ARR array using a while loop. For each element in ARR, we check if it exists as a key in our map. If it doesn't, that means the current element cannot start any valid piece, so we immediately return false. If it does exist in the map, we retrieve the corresponding piece array. Once we have the matching piece, we compare its elements to the corresponding segment in ARR. Using a for loop, we iterate through the piece and verify that each element matches the respective element in ARR. If there's a mismatch or if the segment extends beyond the bounds of ARR, we return false. If everything matches, we move the index I forward by the length of the piece to skip over the verified segment and continue checking the rest of ARR. Finally, if we successfully check all segments and find no mismatches, we return true to indicate that ARR can indeed be formed by concatenating the pieces. To solve this problem, we begin with example 1. The input array is ARR equals 85, and the pieces array is pieces equals 85. First, we need to create a mapping called piece_map, where the key is the first element of each piece and the value is the entire piece. In this case, piece_map becomes 85, 85. We also initialize an index variable, I equals 0, to iterate through the ARR. Now, in the first iteration, we check if the current element of ARR, which is ARR, I equals 85, exists in piece_map. Since it does, we retrieve the piece associated with it, which is 85. Next, we compare the segment of ARR starting at I and spanning the length of the piece with the piece itself. Here, the segment is ARR 0:1 equals 85, and it matches the piece 85. Since they match, we move I forward by the length of the piece, updating I to 1. Finally, as I now equals the length of ARR, the iteration ends, and we return true because all segments matched successfully. Now let's look at example 2, where ARR equals 15, 88, and pieces equals 88, 15. First, we create the piece_map, which becomes 88, 88, 15, 15, based on the pieces given. We again initialize I equals 0 to start iterating through ARR. In the first iteration, we check if ARR, I, which is 15, exists in piece_map. It does, so we retrieve the corresponding piece, 15. We then compare the segment ARR 0:1 equals 15 with the piece, and they match. This allows us to move I forward by the length of the piece, setting I equals 1. In the second iteration, we now check if ARR, I, which is 88, exists in piece_map. It does, so we retrieve the piece, 88. We compare the segment ARR 1:2 equals 88 with the piece, and again, they match. We move I forward by the length of the piece, updating I equals 2. At this point, I equals the length of ARR, so the iteration ends, and we return true since all segments matched successfully. Now consider example 3, where ARR equals 49, 18, 16, and pieces equals 16, 18, 49. First, we create the piece_map, which in this case becomes 16, 16, 18, 49. We initialize I equals 0 to iterate through ARR. In the first iteration, we check if ARR, I, which is 49, exists in piece_map. Here, 49 is not a key in piece_map. As a result, we immediately return false because the current element of ARR cannot be matched to any piece. This concludes the process for this example, with the final output being false. To analyze the time complexity of our solution, we start with the process of building the hash map, which we call piece_map. Here, we iterate through the pieces array, and for each piece, we insert an entry into the hash map. Since there are k pieces and we add one entry per piece, this step takes k time. The length of each piece doesn't directly affect this operation, as we're only concerned with the number of pieces. Next, we traverse the input array ARR using a pointer, I. For each element in ARR, we check if it exists in the hash map, which is an O1 operation on average because hash table lookups are constant time. If the current element is found, we retrieve the corresponding piece and compare it with the subarray of ARR starting at the current pointer. This comparison takes m time, where m is the average length of a piece. After the comparison, we move the pointer forward by the length of the matched piece. Since every element in ARR is processed exactly once, the traversal of ARR takes n in total, where n is the length of ARR. Now let's combine these steps to determine the overall time complexity. Constructing the hash map takes k, and traversing ARR with comparisons takes n. Typically, the number of pieces, k, is much smaller than the length of ARR, n. This means the time complexity is dominated by the traversal of ARR, resulting in an overall time complexity of n. Shifting to space complexity, the primary contributor is the piece_map hash map, which stores one entry for each piece. If there are k pieces and the average length of each piece is m, the space required for piece_map is proportional to the total number of elements in pieces, which is k*m. Other variables, like the pointer I and the temporary piece, only use constant space, 1. Thus, the overall space complexity is primarily determined by the hash map. When we consider the overall space complexity, the hash map remains the dominant factor. With k pieces and an average length of m, the total space usage is k*m. Now let's briefly compare our optimized solution to a brute force approach. A brute force method would involve checking all permutations of the pieces to see if they can form ARR. Since there are k pieces, this could lead to a factorial time complexity of O(k), as every possible arrangement of the pieces would need to be evaluated. In contrast, our optimized solution uses a hash map to directly map the first element of each piece to the piece itself. This allows us to traverse ARR just once and perform efficient lookups, significantly reducing the time complexity from O(k) to O(n). This highlights the efficiency of our approach. Let's examine the best, worst, and average case scenarios for our solution. In the best case, every element in ARR matches the first element of a piece, and the pieces align perfectly. Here, the solution processes each element of ORR exactly once, resulting in a time complexity of O(n). In the worst case, elements in ARR might not match any piece, or mismatches could occur during comparisons. Even in this scenario, the time complexity does not worsen because each element is still processed at most once, keeping it at O(n). On average, the solution efficiently performs lookups and comparisons thanks to the hash map, and the complexity remains O(n). To mathematically prove this, we see that the traversal of ARR is linear, taking O(n), while hash map operations like lookups and insertions are O(1) on average. Subarray comparisons contribute O(m) per piece, but since each element in ARR is processed once, the total contribution is still O(n). This confirms that the final time complexity is O(n), and the space complexity is O(k*m). When tackling this problem, there are several common mistakes to watch out for. First, it's easy to misinterpret the subarray matching requirement. A typical error is assuming that the elements of pieces can be rearranged or reordered to form subarrays in ARR. This is incorrect because the problem usually mandates that the subarrays in pieces must appear in exactly the same order as they do in ARR. Another common pitfall is ignoring boundary conditions, such as handling cases where pieces or ARR are empty, or when subarrays in pieces do not exist in ARR. Overlooking these edge cases can lead to runtime errors or incorrect outputs. Additionally, some people mistakenly assume that all elements in ARR in pieces are unique, which can lead to faulty logic. Duplicate values or overlapping subarrays require careful handling to ensure correct results. Lastly, incorrect index tracking is another frequent issue. When verifying subarray matches, losing track of indices can cause skipped elements or mismatched subarrays, especially when the subarrays in pieces have varying lengths. Taking the time to address these potential mistakes will help you write a more robust solution. Another mistake to avoid is relying on inefficient brute force implementations, such as using nested loops to check subarray matches. This approach can result in O(n²), or worse time complexity, which is unlikely to scale well for larger input sizes and may even violate the problem's constraints. To succeed in an interview setting, it's crucial to understand the problem statement clearly. Pay close attention to constraints like the ordering of subarrays in ARR n pieces. Optimizing beyond brute force is key, and one way to do this is by using a dictionary to map the starting elements of subarrays in pieces for quick lookups. During an interview, communicating trade-offs is just as important. If you start with a brute force approach, be sure to explain its limitations and then iterate toward a more optimized solution. Emphasize the importance of edge cases, such as empty inputs, duplicate values, or non-matching subarrays, as this demonstrates thoroughness. Finally, point out how this problem relates to broader concepts like subarray matching, sequence reconstruction, or the general use of hash maps, as recognizing patterns often impresses interviewers. This problem also shares similarities with other coding challenges, which can provide additional context for solving it. Examples include LeetCode 448, which involves finding all numbers that disappeared in an array, or LeetCode 350, which focuses on the intersection of two arrays. Additionally, LeetCode 205, which tackles isomorphic strings, and LeetCode 560, where the goal is to find subarrays with a sum equal to k, are other related problems worth exploring. When considering alternative approaches, a hash map can be a highly effective tool. By storing the starting element of each subarray in pieces as dictionary keys, you can achieve efficient lookups. This method has a complexity of O(n) for traversing ARR and O(m) for building the dictionary, where n is the length of ARR and m is the total number of elements in pieces. While this requires extra space for the hash map, the performance gains often make it worthwhile. Another option is the two-pointer technique, which involves matching subarrays in pieces with segments of ARR. This method can also achieve O(n) complexity when implemented correctly. However, it can be more challenging to implement, especially when subarrays vary in length or overlap. Sorting and matching is another approach you might consider, but it comes with significant trade-offs. The idea here would be to sort both pieces and ARR and then compare their segments. However, this approach is generally infeasible for this problem because sorting alters the order of elements, which directly violates the constraint that subarrays in pieces must appear in the same order as they do in ARR. Unless the problem explicitly allows reordering, this method is unlikely to produce the correct result. It's important to remember that while sorting can be a powerful tool in many algorithms, it's not suitable in scenarios where maintaining the original sequence is critical. Thank you for watching. Today, we explored the problem of array formation through concatenation. We reviewed an efficient hash map-based approach, analyzed its complexity, and discussed key takeaways. Don't forget to practice similar problems and stay tuned for more tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!